Here is Eli Holderness. Eli has been in tech since the beginning, being released back into the wild from studying math at the university 7 years ago. They've spent their time working in industries ranging from telecoms to biotech to analog circuit design, continually getting nerd snipped along the way. These days, they are a freelancer who speaks at the conferences, run workshops, and learns whatever they want. In their spare time, they like to play video games, knit and sew, and hang out with their cat. Eli will be talking about pointers in Python. It's more likely than you think. So please welcome Eli.
It's okay. Just making sure I'm going to be loud enough for you all.
Can you try?
Hello. Hello. I hope you've all been having a wonderful time so far today here at PyCon Slovakia. I'm honoured to be here and honoured to have so many of you here today to listen to me talk about memory management. So yeah, that is the topic of today's talk. I'm going to go through, it's like 3 main sections, and it's going to be a whistle-stop tour of how Python manages objects in memory. So first, I'll talk about what pointers are, a kind of abstraction that I'm going to use in this talk. I'm not using them in exactly the same way that what C has as pointers or C++, but you know, I'm going to talk about what I mean when I say pointers. I'm going to talk about what the ID of a Python object is and why it matters, where you'll see this come up in your code. And finally, I'm going to talk about how CPython, in particular, knows when you are done with a given object in memory and how it gets rid of it. So, what is a pointer? Well, it's something of an abstract concept, so I'll give you an example. Here's me. Here's a pointer to me. I have a name. My name is Eli. I'm also, God help me, on Twitter, and you can find me there. I'm also on Discord, and I have a Discord username too. There are lots of other ways that you might choose to refer to me as an individual. And pointers in Python are a bit like this. One example of pointers is when you name your variables. Variables are entries in the namespace, and I'll talk more about what the namespace actually is. And they point at objects in memory. So if you have an object, and you've got a name for it, my class instance, and then you have the actual object that lives in memory. And what I'm calling a pointer is that connection between those two things. The fact that you can use that name to access that object in memory. So, some concrete examples. This is what I mean by the namespace, and this is actually a well-defined term and not one I made up for this talk. Let's say we've got 2 variables, and we're just running a Python interpreter here. You can see if something is in the namespace using the globals built in. So if you call this built-in, it'll print you out a big, long dictionary of all the things that are in the global namespace. And you can see, in particular here, that the variables we just defined are in that dictionary. They are in the namespace. And we'll use this later when we're talking about removing objects from memory. One example that I'm going to be using quite a lot through these talks is lists. And lists are interesting because they are Python objects that also contain pointers to other Python objects. So if we have a list called A, and it has 2 elements in it, one of them is a string, and one of them is a number, the string and the number are their own objects, and the list is also an object that contains pointers to them. And this makes it very nice for illustrating lots of examples of how Python handles objects in memory. So, the first thing I want to talk about is pointer aliasing. Has anyone come across this term before? Please tell me, by the way, if I'm speaking too fast. I tend to speak very fast, and I'm aware that English is my first language. I'm aware that for many of you it will not be. So pointer aliasing is a behavior that you can see, it's a confusing behavior that Python exhibits. And when I give you an example, you might recognize it. Let's start with a list A, and it has 3 elements in it, my cool list as strings. We define it, we print it out, all is well. Now, let's say I want to have another version of this list. Well, I could just say, well, let B be equal to A. But I want B to be my awesome list, not my cool list, right? And so we do that, we change the second element of it. Does anyone want to guess what's happened to A? Anyone know this? It's also been changed. Even though at no point did we say change A. directly. We did it implicitly. And this can be confusing, especially to people who are new to Python, because they say, well, I didn't change A. Why has A changed? And this is because A, the list, is an object in memory. And when we said B is equal to A, we made a new pointer to that same object. So when we're accessing B, we're manipulating the same memory, the same Python object, as A. So when we look at A, the underlying Python object has also changed. Now, if we don't want this behavior, if we wanted truly to have another copy of a list, we can do that because lists have a copy method on them. So if I wanted to actually have another list and change it without changing the original, I can do this. I say C is a copy of A, and then when I do the same thing, I change C to be my amazing list. We can see that A has not been changed by that. It's still like it was before. And this is great because it means that, you can make a copy of your list and mess around with that without changing the original. And this is wonderful. However, what if you had pointers within your pointers? What if you had a list of lists? So here we can see I've now defined a new thing, A, and A is a list, and its first element is another list, and I've just added a number in afterwards just to make it extra clear that there's an outer list and an inner list. We don't need to use that number. So we're going to do the same thing again. We're going to say, OK, I would like to make a copy of this so that I can mess around with it without changing the original. So I do exactly the same thing. I use the copy method. And then I say, I'd like to amend that inner list. I'd like to add Charlie to our list of names. And so I do that. And I've changed B. And we used the copy method, right? So we shouldn't be messing with our original list, A. Does anyone want to guess what happens here? It is also changed. We have also changed A. And this is because the copy method copies the outer object, makes a copy of that. But anything that's inside, it still points at the same thing. So what we did was we copied the outer list, but the pointer that was inside that list that pointed to another list, it's still pointing to that inner list. And there are some diagrams that should make this a bit clearer in a moment. What if I did want to make a copy of my list within a list and maybe more lists inside that? What if it was pointers all the way down and I want to make an entirely new structure? Well, we can do that. Python has a built-in method, built-in the copy library, deep copy. And what you do is you call this, it's not a method on a thing, you have to call it itself. It's, so the syntax looks like this. And you say, OK, we take our original A and we make a deep copy of it. And then when we do the same thing again, we want to amend the inner list that's like one layer down. We can do that, and it doesn't change the original. Everyone with me so far? Cool. So diagrams. Diagrams make everything easier to understand. When you do equals, you're simply making a new pointer to the same object. On the left here, you've got A pointing at the list object, and then the list object pointing at the things that it contained, its elements. And then when we set B is equal to A, all we're doing is we're adding a new arrow here, a new pointer. But the actual object is the same thing. If we do copy, like the list copy method, we make this is all new. We've made a new pointer to a new object, but the pointers within that new object still point at the originals one layer down. And that's why when we had a list within a list, we used the copy method, and we changed something, it was still reflected here. It was still pointed at through this object. What deep copy does is it makes a copy of everything, an entirely new set of objects. So there's no connection between what B is and what A is, what they're pointing at. So now, if I do a deep copy, I can do whatever I like to this, and it will never be reflected in anything that I can access through the A name. So that's the difference between all of these three ways of introducing variables into your namespace. Depending on what you want to do, you might want some level of pointer aliasing, but maybe you're working in a very memory-constrained space and you don't have space to have lots of copies of something floating around. But in general, this is pretty useful because it means you can make an entirely new copy of something and you won't be confused by pointer aliasing. Now, in the abstract, I promised you some tuples behaving badly. This is an example of Python doing something unexpected. Does anyone know the example that I'm about to send? I can see some people, I can see some people sort of smiling. Okay, so, right, a tuple is an immutable Python object. That means that once it's defined, it cannot be changed, right? That means that whatever you put in, let's say, the first element of a tuple, that pointer has to point to the same Python object. That pointer cannot be changed. It cannot be changed to point to anything else. But what if the thing that it's pointing at changes itself? What if the thing it's pointing at is a mutable object that can change? This is what that looks like. We have A here, and it is a tuple, you can see, because it's got the round brackets. And inside the tuple, we have a list, which is mutable, and a number, which isn't, an integer, which isn't. And we can look at that first object that's a list by saying A0, just the same syntax as we do for lists. And with lists, we have things like the append method, which we can use to mutate the list in place. So if we want to make our list longer, we can do that, no problem. The list has just been put in place, changed in place. Another syntax for doing the same operation to a list is to do this, right? You say, okay, I've got my list, that's A0, and now I want to add 5 to the end of it. This is a syntax for doing the same operation. Except when we try it with this, we get an error because it says we've tried to assign to the first element of the tuple. And this is fairly expected, right? Like this has got an equals in it. We can't do assignments to this thing because we can't assign to objects in a tuple after they've been constructed. So far, so reasonable, except when I print out this thing, it does have the 5 in it, even though Python said we had an error. Python's like, I'm not going to do it, but I did it, but you can't do that. So what's happened here? Well, it's to do with this operator, the plus and the equals. What this operator does is it adds the object to the list, and then it reassigns that A0 to the list. With a list with a mutable type doesn't actually do anything. It's assigning the list back to itself. But it still trips up the error handle. Like it still says you can't do that because you're assigning to an element of a tuple. The reason that this operator is useful is when you're using it with types that are not mutable. So if I was going to do this with a string, so like my string, and then I do plus equals is cool, you'd have to make an entirely new string object to put that new string into because strings aren't mutable. So that's the case where this plus equals operator actually does something interesting and useful instead of just confusing. So if you're ever trying to mutate objects within a tuple, make sure you're doing it truly in a way that is mutating in place and not secretly doing an assignment as well, because you can't assign to things in a tuple. Tuples behaving badly. Has anyone run into something like this in production? Has anyone ever seen this kind of bug before in the wild? It's mostly like a sort of toy example that people give exactly to illustrate how Python does memory management. But as far as I know, this is still absolutely true in Python 3.12. So, right. If we come back to this paradigm that we have, right, this situation where we've got an element, we've got an object A, let's say it's a list and it points at some other things, and we have another variable name that's also pointing at the same thing. This can be confusing. That's what pointer aliasing is. How can we know if this is the case? If all I know is that I've got A and I've got B, how can I know if they're actually pointing at the same thing or if they just look the same? This is where object IDs come in. Object IDs. Now Python, every implementation of Python has to have an ID built-in function. You can call this on an object, and what it does is it returns you a number. That number is unique for that object in memory. It doesn't change. For that same object in memory, as long as that object exists, you can call this function, you'll get the same number for the lifetime of that object. We'll come back to lifetimes later in the talk. And there are lots of different ways of implementing this. Lots of Python implementations use the object's address in memory. Because if we go back, where an object lives in memory, well, it's unique. Two things can't live in the same place. It is constant, because as soon as you move the thing, it becomes another object. And it will be true, that will be true as long as X is in memory. So the address in memory makes perfect sense as a way to give your objects identities, IDs. However, this is what CPython does. Not every language can do this, because not every language is implemented in a way that gives it access to memory addresses. For example, Sculpt, which is a JavaScript, a Python to JavaScript transpiler, can't do this because JavaScript, the Java virtual machine, does not have access to memory addresses. So instead, what it does is when you call the ID function on an object, it generates a number. Like, I think it actually might just count up sequentially, assigns it to that object, and then that object has that ID for the rest of its lifetime. But it's arbitrary. It's just used for the places that you would need to use ID. So where do we use ID? Well, we can look at the IDs of some object. If we go back and we make a list, we can call this. And this is in CPython. You can tell this because of the sort of specific way that this might look more familiar to any C programmers if it was in hexadecimal. This is just an address in memory. And if we do the thing we've done before, and we say B is equal to A, and we look at the IDs of each of these, we can see they're the same. They're the same object in memory because they live at the same place. They have the same ID. And if we do the thing we've done before and say C is a copy of A using that list copy method, they're different now. That's a different object in memory because they have different IDs. When we do comparisons, in order to know if two objects are the same, this is where the is comparator is useful. If you do A is B, which will return true or false, that's exactly the same as saying, are their IDs the same number? That's what's happening under the hood. Is just syntactic sugar to let you do this comparison more naturally, more easily. So we can see this in action. We do our familiar setup where we've got A, a list, B, another pointer to that list, and C, a copy of that list. And if we look at what happens when we compare them, A is B, well, that's true. They have the same ID. They're pointers to the same object in memory. C doesn't have the same ID. It's false. But that's not the only way we have of comparing objects in Python. We also have the doubles equals operator. And if you call that on these objects, you'll see here that A is equal to C in some way. And this can be really confusing. You might think that these things are doing the same thing, but they're not. So what is that doubles equals actually doing? It's using a magic method under the hood. That's what it calls into. That's what it relies on. So what is this magic method? Underscore, underscore, equals, underscore, underscore. You'll be probably familiar with some magic methods in Python already. We've got double underscore str, which defines how the string, the str built in, interacts with an object. We've got del, which we'll come back to later when we're talking about garbage collection and removing objects from memory. And of course, init. Equals is just another magic method. What it does is when you define this magic method on the class, it defines how that doubles equals comparator interacts with instances of that class. This is just a bit of code that we can mess around with. So we could write a class like this. I've defined a new class object, and I've defined this magic method on it. And I've just said, look, fall back to the ID-based comparison. Are they actually the same object in memory? And it will return true or false, exactly as if you just used is instead of double equals. This is the default implementation for any user-defined class in Python. This is exactly the same as if I had not defined this method. That's just what Python does by default. And that's fine and reasonable, but we can play around with it a little bit. We could say, okay, what if I have a class where it has an attribute, it has a name that we'll use to tell instances apart. But when I compare it to another instance of the same class, I want you to always return true, right? If you've played around with magic methods in Python, you know that this can lead to some funny behavior. And the funny behavior in this case is that let's make two instances of that class, call them A and B, we give them names, and you can see that they have an attribute that's not the same. A's name is not the same as B's name, but they are equal, apparently, because that's what we defined that magic method to do, just always return true. This is obviously not very sensible. There aren't many situations where you'd want to do this. So what if we went the other way? What if we said, okay, I'm going to define a class, and it never returns true. No matter what you compare it to, it's different than everything in the world. It's even different than itself. Because that's what it's doing. That's all that thing is doing, is it's calling into this method and saying return false. And that's that false that you're getting there. So playing around with magic methods, fun, potentially dangerous, potentially very confusing. Now, ID, the object's ID, I mentioned that it's the same for the lifetime of an object. And what that means is the amount of time that that object lives in memory, the amount of time that that object is accessible and is stored in the memory that the Python interpreter has access to. And when you get rid of an object, when an object's lifetime comes to an end, Python must free that memory, must tell the interpreter, okay, the interpreter says, okay, I can rewrite to this memory. I can write over it with something new. And Python knows that it needs to be, that it can do this in two ways. The first is with reference counting, which we'll go through. And the second is garbage collection, which we will also go through. So reference counting is the first easier to understand method of knowing when Python is able to say, we don't need that object anymore, we can get rid of it, we can write over it. So for each object, Python will keep track of how many pointers point at that object, how many of those little arrows lead to that object. If there are no arrows pointing to that object, then there's no way to access it, there's no way to manipulate that memory, there's no way to use that object. It's useless, so Python can get rid of it. Its reference count falls to 0, and Python says, okay, we can write over that object. And we're going to meet another magic method that I mentioned earlier that's going to let us have a little bit of visibility into this process. So this is another magic method that you can define on a class. And it is called when an object is about to be removed from memory. It's called a finalizer. It doesn't actually handle the removing of the object from memory. Python does that for you. But this lets you do things like maybe you opened a file as part of creating this object and you want to close that file out. Maybe there's some other kinds of cleanup that you want to do when this object is being removed from memory. And that's what this is for. We're not going to do any of that. We're just going to make it print something. So we've come back to a class that has a name so that we can tell instances apart. And when it's about to be removed from memory, we'd like to know this. We'd like to see this. So we've just said, hey, please print something and tell me that you're deleting this object. Now, if we actually make an instance of this class, we've got Dave here, and then we've deleted him. And we can see that Python has printed out for us, it's deleting him. So we're going to use this example to have a bit of visibility into this process. Now, if I've made Alice, that's an object in memory, and I've made another pointer to Alice by doing b equals a. That same thing again, except also Alice equals Alice. And now if I delete the first name, Python doesn't print anything out. I'll have to delete the second name too. That second entry in the namespace also had a pointer to this object. But once I do, Alice can be removed from memory because at this point, here's Alice, and she has a reference count of 1. Now, by assigning a second name at this object in memory, has a reference count of 2, back to 1, now it's at 0, and she's gone. With me so far? Cool. This is when it gets interesting. So, let's make, we come back to the idea of is something in the namespace, sorry. We're looking at the namespace here by calling that globals. And we can see that our class definition, because defining class definitions are also objects in Python, we can call this and it will instantiate an instance of this class for us. And one way to check if something is in the namespace is just by calling this, saying, okay, is this in globals? And it'll say true. And we'll use this to check when things are in the namespace or not. So let's make 2 people, 2 instances of our named class. We've got Jane and we've got Bob. And these are just objects in Python, and we can arbitrarily give them attributes like friends. So let's make Jane and Bob be friends. And what we're doing here is we're making these 2 objects point at each other. And we can see that both Jane and Bob live in the namespace. Now, if we delete Jane and Bob, those 2 names, those entries in the namespace, they are not deleted. We don't get that print statement, right? even though they're not in the namespace anymore. They're isolated from the namespace, but they still point at each other, so their reference counts aren't 0. But we can't access them from the namespace. We can't use them anymore. They're inaccessible to us, but they're still there taking up memory. So in diagrams, this is what happened. We've made these two objects, and you can see each of them has a reference count of 1, and we make them point at each other, these pink pointers here. And now each of them has a reference count of 2. Jane points here, and Bob eventually also points at Jane. And then we delete them. But even though there are no connections from the namespace, these 2 pointers still exist. Their reference counts aren't 0, so reference counting on its own cannot know that these objects need to be deleted, even though they're useless to us now. Can't get at them anymore. So reference counting on its own isn't sufficient. You can still end up in this situation where you have objects clogging up your working memory that are useless to you. And this is where the garbage collector comes in. And here I start focusing specifically on CPython. I think not every implementation of Python even has a garbage collector, but don't quote me on that. CPython does, and we will be looking at it. What the garbage collector does is it's a process that's always running while you have a Python interpreter open. It detects these cyclic isolates. And what we made just now, it was a cycle of objects that pointed at each other, isolated from the namespace, and those are called cyclic isolates, and they're a problem. It detects them. It calls their finalizers, and if there's a del method implemented on those objects, it will call them, and then it will start breaking the cyclic references. It will start removing the pointers. It would remove the thing that the pointer from Bob to Jane and from Jane to Bob. At that point, each of those objects has a reference count of 0 because those references got removed, and reference counting can take over and clean them up. Now, there's a little asterisk here because at this point, the process can go wrong. But let's see it go right first. We can actually look at the garbage collector. It's a module in the standard library, import GC. And the garbage collector doesn't track every object that Python includes. These are all tracked by like a string. It's tracked by reference counting because things can point at it, but a string can't then point at anything else. It can't contain pointers. It's not a container type. So it can never form part of a cyclic isolate, right? It would end there because a string can't point onwards. So the garbage collector doesn't need to care about strings. It only needs to care about objects that can point at other objects, like lists, right? This is tracked by the garbage collector. And so is any instance of a user-defined class, because we can define arbitrary attributes on them. They can always point at other things. So what the garbage collector does is every now and then, and you can trigger this manually, it will use an object's traversal method, and every object has this. A traversal method, what it does is it looks at everything that the object points to. And then it goes to every object that that object points to and looks where they point. And in this way, it can build up a directed graph of all the objects in memory that could form part of a cyclic isolate. And if it ever gets back to where it started, it knows that that object is part of a cycle, right? So this is that traversal method. You've got a list, and you say, what does this list point at? And it points at these 2 objects. This is not the same list as this. This is just the output from that method containing the same objects. That's not particularly important, but it's just that's why it's transposed here, because this is not actually the same list. But it said, okay, this thing points at these 2 strings. So what we do again to illustrate this is we'll set up our cyclic isolate again. So this is just what we did before, got our named classes. We've given them some names, Jane and Bob, and some pointers from the namespace, also Jane and Bob. And then we've removed those pointers from the namespace, and we have a cyclic isolate. And we've imported the garbage collector, and we've manually triggered collection. And this is the point at which it goes, I found a cyclic isolate. I can break those references. Now the reference count falls to 0. We get our nice print statements. And this number at the end is 4, and that's the number of objects that it cleared out from memory. So each object also had a name, the string that was their name. So 2 objects, two things per named class object. So we've got 4 things to remove. Bingo, done, sorted. this is where it starts to get broken, because you can write your own del method to interfere with this process, and we are going to do that now. Here we have a bad class that also has a name, but I've written a del method for it. And instead of just printing, which we still do, I've said, okay, let's define a global variable, which is a great thing to do for fun if you'd like to break your programs. And I've said, okay, make a new entry from the namespace, from the global namespace, and set it to be equal to the object that I'm dealing with right now. If we go back to our example, and instead of using our named class, we use our bad class, and we set up a cyclic isolate for this, we call the garbage collector, and it gives us those print statements, but it doesn't delete anything from memory. And this is because before it can remove things from memory, it needs to call their finalizers. And what those finalizers did was they reached back out into the namespace and created a new pointer to that object in memory. Now that object is no longer isolated. And the garbage collector can know this, and it can say, okay, we've still got an object in memory, right? Because it's being pointed at from the global namespace. We've got a new name, person. And it turns out the person is Bob. And this is because Bob was the one that got deleted second. So the finalizer ran, that's why we got that print statement. But the other thing the finalizer did was set person equal to Bob. And so Bob still exists, that object in memory, and so does Jane, because Bob pointed at Jane, right? Here, we can see what we've done. We've got that cyclic isolate, but after Bob's finalizer ran, we also had this, and that stops, sorry. That variable stopped the garbage collection process, because now we can access these, so they can't be garbage collected because they're no longer isolated. Even though Jane doesn't exist in the namespace and Bob doesn't exist in the namespace, person does, and it keeps those references alive. However, finalizers can only ever be run once per object, and the garbage collector keeps track of this. The person object, which is Bob, used to be called Bob, has had its finalizer run, and you can check this. And if we call garbage collect again, we have to delete that pointer from the namespace, and we run the garbage collector again. It cleans up those objects, and it does not run their finalizers again. So we don't get those print statements, but we do see that the objects were collected from memory and deleted. And this finalizers can only be run once to prevent exactly this kind of abuse, essentially. However, you can still get around it if you define a new object that's never had its finalizer called. So this you could never fully delete. Once you've instantiated an instance of this class, you will always have an instance of this class in memory, because every time you try and delete it, it'll make a new one. Don't do this either. Yeah, fun with finalizers. This breaks garbage collection. Don't do it. Right, we are now at the end of this whistle-stop tour. I'm aware I've run a couple minutes over. I'm sorry for that. But we have learned what pointers are and where you'll find them. We've learned why is and double equals are different, why you might want to use them in different scenarios. And we've talked about removing objects from memory and how you can mess around with it. Thank you so much for your time and attention. That link there will take you to a feedback form where you can leave me just anonymous feedback. So please do. I always love to hear how I've done and if I can make things better. I hope you've learned something. I hope you had fun, and I hope you have a fantastic rest of your time here at PyCon Slovakia. Any questions, or do we want to all go and get coffee?
Yes, we have a few questions. So, what is the difference between pointer aliasing versus pass by value, pass by reference concept we know from other programming languages such as Java? What does it make unique?
So as I understand it, in Python, you are always passing by reference because we never actually work with the objects in memory. My background is I did a bit of C programming before coming to Python. And so this would be the difference between like you've passed in like an ampersand thing versus, the star, the asterisk. Good question. I don't know if I can answer. I don't know enough about passing by value and passing by reference in other languages to make a good comparison. I think in order to answer that question, you'd have to really go and understand what each of those languages were doing in terms of how they handled memory. But my first instinct is to say Python is always passing by reference because you're always just passing around variable names.
Is garbage collector included in the standard libraries, or we have to install it?
CPython, it is included in the standard library. I think it is part of the Python, like reference, the Python standards. So in theory, all implementations should include it, but I'm not sure if that's actually true. Not every implementation of Python follows the standards. But no, CPython, which almost everybody will be using almost all of the time, has it included. No installation required. That's vanilla Python.
I like pythontutor.com. It visualizes these things. Do you know similar tools?
I have never used pythontutor.com. Does it? What is the person who asked this? What does PythonTutor do for you?
It's an interactive debugger on the web.
Oh.
Step by step run short Python code, and it will show you the arrows between objects.
Oh, that's cool. So an interactive debugger on the web that will show you visually these things. Oh, that sounds really cool. It also sounds like I probably should have used that instead of drawing boxes in Google Slides. It's a bit stale and old. Okay. I don't know of anything similar. I have used things like GDB to debug, but mostly what I did was I read the C definitions of a lot of these things to understand it. Right. Are init and del methods something like constructors and destructors in C++? So the del method doesn't actually deal with the removal of the object from memory. It's just something like you can not define it at all. But I think so. I don't actually know what the destructor does in C++. I'm sorry. I would say go and sort of look at actually what C++ is doing under the hood when it calls these things, and compare.
The questions keep coming. So okay.
What was the performance cost of the garbage collector? Was the previous one?
Yes, I accidentally.
Yeah. Depends on your use case. If you're creating a lot of objects and have a lot of potential for cyclic isolates to arise, then it will probably have a higher performance cost, but you might have a higher performance cost to turn it off because you're clogging up your memory with lots of cyclic isolates. If you're in a scenario where you can somehow be sure that you'll never create cyclic isolates, in theory, you could safely turn it off. Yeah, I know that there are performance enhancements that are baked into the garbage collector that you can configure. So it has this concept of generations of objects. So once an object has been looked at by the garbage collector once, it moves up a generation. And there are different ways that you can use this to make the garbage collector behave differently. There's also a thing you can do called gc.freeze, which says everything that's currently in memory, never get rid of that. I want to keep that forever until the Python interpreter dies. I don't know when you'd want to use that, but you can do it.
So when does the garbage collector run if we are not manually calling it?
It depends. After a certain threshold of items created and destroyed, I believe. This is one of those things where like the whole generations thing comes into play, and like there are certain thresholds for the generation that's never been looked at by the garbage collector. That is configurable in Python if you want. So if you don't want to turn off the garbage collector, but you want it to run only much more infrequently than it would normally, you can do that too.
I think we ran out of the time, but if
these are great questions, thank you.
If you want, we can have a minute or two more. We have now
I'm happy
is
to
15
stay as
minutes
long
break,
as
if you want to answer the questions, and we can be a bit longer, if you don't mind.
Is it possible to have a memory leak in a Python app without using the global keyword? In CPython, you can call directly into the C API. So yes, basically, if you really want to break things in Python, you usually can. There's that whole thing about it's a language for grown-ups, and there are guardrails, but if you want to break the rules, you can. So I think that is certainly possible, even if I don't know how to do it right now. I think it will probably take me about 5 minutes to find out. So, yes. And I would say that the example I showed at the end is not so much a memory leak. Well, it would be a memory leak for each object that you instantiated. And the object on its own, if you just instantiated one, that memory leak is not going to grow larger. You'd have to instantiate another new object, essentially. Yeah.
So why does the garbage collector explicitly call del method instead of just breaking up the pointers and wait for auto trigger by reference counter?
Because in some scenarios, you might want to make a new global. You might want to say, actually, if this is part of a cyclic isolate, something's gone very wrong and I want to keep the object alive so I can debug. There might be reasons why you do want to intervene at that point where it's about to break up a cyclic isolate, but it's called all their finalizers. That's why that is left in there. It's sort of to give you as a programmer the chance to say, hang on, no, I want to do something weird and special because my use case it requires it. Yeah.
And the last question is there a way to force garbage collector to drop everything user-defined?
You can. I'm not sure exactly what the status of it is. There was a bunch of stuff in some of the recent changelog for like maybe 3.12 that was to do with you can explicitly tell the garbage collector to untrack things. I don't know how you would do it as a blanket stop caring about user-defined classes. I don't know if you can turn that off as a behavior, but for given instances, given objects, you can tell the garbage collector to stop tracking it. Yeah, good question. I don't know why you'd want to. But clearly you're not working in a memory-constrained environment.
Okay, that's all. So thank you, Eli, for your talk. It was definitely very
Thank you so
interesting.
much for being a wonderful audience, and have a wonderful rest of your day.
So now we have a 12-minute break. You can return for the next talk that will be in English, and we have a lightning talks board outside. So if you want to do lightning talk, please sign up on the board, and they will be done at the end of the day in the other room. Lightning
talks are amazing. You should do them if you even slightly think you want to. Do it. They're great.